most of us have been in an elevator, okay? Probably all of us have been in an elevator. And do you ever did you ever do this trick like when the elevator, if you're at the top and you're getting ready to go down several floors, maybe you're in a big hotel or a big tall building, and you try to time, you jump, you try to time it just right. And if you time it just right, you kind of get this extra long float, all right, as you're going along. But it only works right at the very beginning like that, okay? So what we're going to do when we get to the end of this is we're going to talk about that situation and what happens and what you feel when you're in an elevator, okay? So we've got Charlie. So this little picture there in the top right is from the one of the Willy Wonka movies. That one's got I can't think of his name. He was in the Pirates movie and stuff. It'll come to me later. But at the very end, there's this really fancy elevator, and they're in there. And let's suppose that Charlie's in there and he's got a certain mass, and they're actually accelerating as they go downwards. Okay, so this is a downward moving elevator and it's accelerating. So what's the normal force between Charlie and the floor of the elevator? Okay, so what we're going to do, and we've got to make our sketch first, but I want to come over here and I want to put some forces on Charlie. Charlie's a little guy, of course, so he's got some weight. And then there's a normal force pushing up on him here. Okay, so we've got those two things just like that, all right? So that's probably sufficient for my sketch, okay? I should do a free body diagram, though, okay? That can be useful. Come along here. And I've got the normal force. I've got my weight here, just like that. And let's go ahead and put our acceleration on here because that's useful. And the acceleration is down. Okay, the acceleration is downwards. All right, now I should add to my picture just a little bit because we know the mass is 45. It's good to get that out there. And we know that our acceleration downward is 2.5. Just like that. Okay, so I got all that information copied down there. I'm ready to use it. Okay. So, it says, what is the normal force between Charlie and the floor of the elevator? So, in other words, as the elevator pushes upwards on him, what's the amount of that push? Okay, so what's that normal force? So, if we think about Newton's law like a bridge, okay, which we're going to be doing, got kinematics on one side, I got forces on the other. Here you can see it gives us an acceleration, okay? So that's kind of nice. And that's a kinematics piece of information. Doesn't give us any other information other than mass, but that's just a mass value. So we're going to end up moving from kinematics information to try and figure out forces based on that. And the way we do that is by focusing on the value of the acceleration itself. That's how we cross that bridge. Okay, so let's look at our equations. Fx is max. Okay, and then I've got Fy is may. Okay, now my x information there actually is not applicable. Okay, I don't have any horizontal forces whatsoever, so that doesn't even matter putting that in there like that. So then I've got my vertical forces, and I can write those in there. So I've got N minus the weight is going to be ma. And again, I'm not going to put y on there because it's our only acceleration, and it seems kind of redundant. So we're solving for n. Let's do a little bit of algebra here. So n, okay, we're going to get ma plus the weight, like this. Okay, now the weight is actually mg. Okay, so let me put that in here. Ma plus mg. Okay, oh, now this is kind of cool. Check this out. I've got an m on each term there, so I've got m onto a plus g. So there's my normal force. That's kind of cool. It's just equal to a m onto a plus g. And it looks just like Newton's second law. I've got a mass and I've got an acceleration and I've got force on the other side there. So that's kind of cool. All right. There are all kinds of reasons to wait as long as possible before you actually put in numbers. Okay. There are a handful of times where it's not, but that's very few and far between. Okay. Resist the urge to put numbers in there. Resist the urge to calculate the weight right off the bat. Okay, we could have done that. Oh, wait, let's go. Okay, immediately 45 times 9.81. We're going to get a number, blah, 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 blah. Okay, but try not to do that. Try not to do that. When I'm teaching the non-calculus, the non-engineering students, I do that because it's mathematically simpler. But you guys are more sophisticated. You need to see this on a higher level. You need to operate mathematically on a higher level. Okay, so get that algebra in there. And then when you do that, you get to see cool relationships like this. Okay, which for the moment might just kind of seem like, well, what's the big deal? But I'm going to show you what the big deal is here. You just hang on. You just watch yourself. I'm going to show you. Okay. So let's now go ahead and put some numbers in here. So my mass is 45 kilograms. My acceleration is 2.5 meters per second, but it's downwards. Okay, it's downwards. All right. Then I got to put my g in here. 9.81 meters per second squared. There we go. Okay, now, right now, some of you might be, what the heck, Cordry? Because you said we got to put the acceleration is down, so we're putting negative there, but we're not putting negative in here. What the heck is going on? Well, what's going on is that, remember, g is like pi. Okay? It's just a number. It can't be positive or negative. It's just whatever that number is. The fact that it's downwards, we put that in way up here. Way up here. When we put minus the weight, that takes care of the direction. Poof, we're done. We're done with it at that point. So all we have to do is just put in our number 9.81. It's cool. If we set it up correctly at the beginning, then it's going to be cool as we work our way through it. Okay, now, once we do that, then let's get some numbers here, and I find that my normal force turns out to be 329 newtons, 329 newtons. Okay, now the actual weight, okay, if we calculate that, which I forgot to do, so I'm going to pull up my other gizmo here, and let's get that really quick. 45 times 9.81. Okay, the actual weight of the thing, if I write that in up here, is 441. Okay, so the normal force is less than his weight. Okay, now under equilibrium conditions, what would have happened is we would have said, when we look at our y forces, some of those is 0, n minus w is 0, and so the normal force is equal to 0. Oh, sorry. The normal force is equal to the weight. Just like that. And that's what we get when the acceleration is 0. Okay? Just like that. But if we're accelerating downwards, you can see the normal force is a little bit less. All right? Now, what's going to happen, or what would happen if instead of the whole elevator accelerating downward, what would happen if the elevator was accelerating upwards? Okay? If it was accelerating upwards, then we would get a positive number right here, and the normal force that we would get would be larger than 441. Okay, then it would be larger. All right. So the nice thing about getting a good algebraic result like this is then it allows you to kind of see what happens. Okay. So if I'm accelerating downwards, all right, then n turns out to be less than the weight. If I were accelerating upwards, then N is going to be greater than the weight. If I'm not accelerating at all, if it's 0, then they are equal. And you can get all that from this beautiful little algebraic relationship that we've got right there. Okay, so let's suppose you're in an elevator, and the elevator is moving downwards. Okay, now what happens in an elevator is that there's a little bit of acceleration at the beginning, at the end. It's very modest, okay, but it's there. But most of the time you're traveling in the elevator, you're moving at a constant speed. Okay, so if you're moving at a constant speed, you're not accelerating, so your normal force is your weight. So if you're just cruising along through there and you had maybe some bath scales, like let's take myself, so I weigh about 180 pounds. So if I'm standing on the bath scales and we're moving along at a constant speed, it's just going to say 180 pounds because I'm in equilibrium. I'm not accelerating, okay? But when the elevator is starting and it's going to go up, then my normal force is going to be larger than my weight, okay? I would be in this situation right here. And in that case, instead of reading 180 pounds, the scale is actually going to go up higher. The little spring in there is going to get compressed more, okay, because the normal force went up. So it might go up to 200 pounds or something like that. I don't know exactly what. Okay, now on my way down, all right, if I'm standing there, it's going to read 180 pounds. But then if the car starts to move down, I've got that downward acceleration. My normal force has to be reduced, and then I'll be in this situation. Instead of reading 180, it might read 160 or something like that. Okay, so it's going to go up or down like that. Now, you feel that inside your body, okay? Your body has ways of sensing acceleration, and it does that. It's really complicated. It's called proprioception, and it's how you can know with your eyes closed whether you're sideways or straight up or upside down. Okay, so you know the orientation of your body. Okay, and that happens through you've got nerves all over your body, and you've got connective tissue. So your liver's sitting in there in your body, and your liver sort of hangs down, okay, because the weight's pulling on it. Now, it doesn't sag a lot, but it sags a little bit, okay? And your body's aware of that position. If you roll to your side, it sags a little bit different position, okay? So depending on whatever position your torso is in, your liver's in there hanging in different positions. And your body learns when you're an infant, when you're a teeny tiny infant, it learns how to take all that information in and make sense of it, okay? So that then you get older and we're totally not aware of it now, okay? After a short period of time, we're totally unaware of all that, okay? But babies are trying to work all that stuff out, okay? They got a lot to do. That's one reason they sleep so much. It's a lot of work, okay? So when you are in the elevator and the elevator suddenly goes up, boom, okay? It has this brief upwards acceleration. Then your liver, just for a moment, your liver kind of goes, woo, and then it goes back to its normal position. And all of your organs do that, okay? Everything in your body goes, woo, just like that, okay? And you can sense that, and that's why you feel that woo kind of feeling, all right? Same thing if you're in the top of, if the elevator is at the top, you're going to go down, okay? Right when it goes down, then, all right, all this connective matter holding your liver in position, it's like little springs, okay? And just like the bath scale changed, these are going to change too. And so your liver kind of it shifts position ever so slightly. And you can tell that, and you get that little bit of woo kind of feeling. That's the same thing that happens to you. We've talked about this before, like on a roller coaster. Okay. So, I believe I talked about that when we talked about the cats falling out of windows. Same kind of deal there. All right. So now let's suppose you're going downwards, and you're going downwards at a constant velocity. Okay. Moving at a constant velocity is no different than standing still. Okay. So if there were no little vibrations inside the elevator, you really couldn't tell that you were moving or not. There'd be no way to know, except for the tiny vibrations and the sounds. You wouldn't be able to tell. You could jump and everything acts just exactly the same, okay? However, if you are actually standing still relative to the building, okay, and you time it just right, you can jump and the elevator begins to accelerate underneath you. Okay, and then it's a little bit further than you were before, and it takes a little bit longer to come back and make contact with it. Okay, but it only works that one time. All right, and it only works that one time because every other time when you jump, you're actually moving downwards already. So even though the floor might be somewhere else when you land, you started out moving downwards. Okay, and so there's actually no difference when it's moving in a constant velocity than if it were standing still. Okay, but if you catch it right when it starts to go, then you can get a little lift there. It's kind of fun. Okay, works the other way too. When you're going up and it starts to stop, if you time your jump just right, you can go like extra far above the floor. Anyway, fun in an elevator. Okay, this is what physics nerds do when they get in an elevator.